In this video, we're going to walk through a proof technique called proof by contradiction. We're going to start out by going over the methodology of the proof and then walking through an example. And after that, we'll talk about sort of the pros and cons of using this proof technique. So here's the idea. Proof by contradiction is a very powerful proof technique. It's one that gets used very frequently. It can show up in all sorts of different contexts. The way it works is we have some sort of proposition P, and we want to prove that this holds, that P is true. What we're going to do in a proof by contradiction is assume the opposite of what we want, assume that P is false. After making this assumption, we're going to argue logically from it. We're not going to make any other assumptions, and we're not going to make any type of incorrect or unsound reasoning. From this false assumption, our goal is to arrive at a contradiction. And remember just that in mathematics, that word contradiction has a very specific meaning. It means a statement that is universally false. The reason that this works is we've argued soundly from a starting point, which was an assumption, and we made only one assumption throughout the entire proof. So if we've argued logically, and there's nothing wrong with the logic, then the only thing that could possibly be wrong is the assumption. And so we conclude that it must be false that P is false, that assumption we made at the beginning. That must be false. In other words, P must be true as desired. That sounds perhaps a little complicated without a concrete example, so let's work through a concrete example. Here's the statement that we wish to prove. We're going to suppose that a and b are integers, and we want to prove if 4 divides a squared plus b squared, then a and b are not both odd. So that's a little bit of a complex statement that we wish to prove. We're going to prove this by contradiction. So figuring out the negation of what our statement is can be a little bit confusing. So before we really begin the proof, let's walk through that a little bit. We're going to assume that we're going to let P represent the statement 4 divides a squared plus b squared. We're going to let Q represent the statement a and b are not both odd. And so what we want to do is prove this implication by contradiction. So let's really be careful about what it is that we're assuming. We're assuming the opposite of what we want, the negation of P implies Q. And if you'll recall, if we want to negate an implication, what we do is replace it with an equivalent statement, not P or Q, and then we distribute the negation via De Morgan's laws. So that means the opposite, or the negation of this contradiction, is an and statement, P and not Q. So we're going to begin our proof by contradiction by assuming both that statement P is true and that the negation of statement Q is true. If you read that all together, what that begins with is, suppose for contradiction that statement P, 4 divides a squared plus b squared, and the negation of statement Q. And the negation of a and b are not both odd is that a and b are both odd. So convince yourself of that and reread the first line. Suppose for contradiction that 4 divides a squared plus b squared and a and b are both odd. Perhaps you can see the versatility of proof by contradiction already. That gives us a lot of assumptions that we can then work with to hopefully arrive at our contradiction. 3 assumptions. 4 divides a squared plus b squared, a is odd, b is odd. The very next step of any proof is just sort of unpacking those 3 assumptions we're actually making. The fact that 4 divides a squared plus b squared means that there's some sort of integer, let's call it k, for which we can write 4k as a squared plus b squared. Similarly, if we use the definition of an odd number and assume that a and b are odd, then we get these 2 other equations, that a can be written as 2l plus 1 for some integer l, and b can be written as 2m plus 1 for some integer m. The next step here is to substitute in 2l plus 1 for a and 2m plus 1 for b, and then to do a fair amount of arithmetic. So let's follow that through. So in the expression a squared plus b squared, we're going to make that replacement A is 2L plus 1 and B is 2M plus 1. And each of those things are squared, so we're just going to expand them out. Now, the very next thing I'm going to do is just regroup some like terms and emphasize that divisible by 4-ness that we have going on here. So, for example, instead of writing it as 4L squared plus 4L plus 1 plus 4M squared plus 4M plus 2, I'm going to combine the two 1s into a 2 over here, and I'm going to put all of the terms with a 4 as their coefficient in the front so that I can factor it out. From here, I'm going to use that other part of the assumption that I made at the very beginning, which is that a squared plus b squared is equal to 4k. So when I combine those two pieces of information, I end up with the equation 4k is 4 times the quantity, L squared plus L plus M squared plus M plus 2. Last but not least, what I'm going to do is put all of the 4 stuff on one side of the equation. That is, I'm going to take this piece right here, 4 times this quantity, and I'm going to subtract it from both sides of the equation. And then again, I'm going to factor out a 4 from all of the terms that have a 4 in them on the left-hand side. So those are steps of algebra that I didn't write out, but the expression that we get in the end is 4 times the quantity, k minus L squared minus L minus M squared minus M is equal to 2. And that might look like a mess, but we're really in a good position at this point to reach our contradiction. Because k, L, and M individually are integers, then the expression that we had on that left-hand side of the equation, k minus L squared minus L minus M squared minus M, is also an integer. I'm just taking differences and products of integers, that's going to remain an integer. Now, the problem that we've reached is that that quantity being an integer means that our previous equation, 4 times that quantity is equal to 2, gives us, according to the definition, that 2 can be written as 4n for some n in the integers, the n equal to that nonsense we had before. That proves that 2 is divisible by 4. However, 2 cannot possibly be divisible by 4, given that 4 is larger than 2. So this is our contradiction, and we conclude, since everything we did up to this point was basically straightforward algebra that we know to be fundamentally sound, that the only possible problem could have been with our assumption. That is, that big assumption we had at the beginning could not possibly be true. It cannot be the case that 4 divides a squared plus b squared with both a and b being odd, or in other words, just to rephrase it back in the terms that the problem was given to us, if 4 divides a squared plus b squared, then it can't be the case that both of these things are odd. So that was a long example of a proof by contradiction, not always the best first example, but one that sort of entails each part of the process that we lined out at the beginning and shows that a couple of things that I'd like to discuss from this point onward. So I'd like to go over just some of the pros and cons of proof by contradiction. And which is a pro and which is a con is somewhat up to you in your own personal proof style, but proof by contradiction is the least structured of all of the types of proofs that you learn when you first begin with proof techniques. So of direct proofs, proof by cases, proof by contrapositive, induction proofs, all of those types of proofs have a lot of structure to them. Proof by contradiction is very minimal in terms of what the structure of the proof is. All that's really required is a clear statement at the beginning that that's the proof technique that you're using. That is, virtually every proof by contradiction will start with, we argue by contradiction, or we proceed by contradiction, just to make it clear that your reader knows what proof technique you're using. And like we had in this example, sometimes you can be proving a very complicated statement by contradiction. It's a niceness to your reader to explicitly state what your assumption is. Since that's the real key, there you're making one assumption, you want to be really clear on the one assumption that you're making and make sure that you and your reader are on the same page. So that's this process that we did at the beginning of the example in this video of working through precisely what the negation of our statement was. So those are the only two things that are really required of a proof by contradiction, other than using valid and proper reasoning. Because of this lax structure, proof by contradiction really allows for a lot of creativity. And that's either said in the way of lax structure allows for creativity and you're really excited about it, or lax structure allows for creativity, meaning there isn't always a great direction for what you should do next after you've made your contradiction assumption. And so sometimes people find that frustrating, that what to do next is not always entirely clear. Another thing that is interesting about proof by contradiction is that although you know that the ultimate goal is to find a contradiction, there's no foresight at the beginning of the problem as to what this contradiction might be. It could really and truly be any contradiction in the world. You could end up showing that 1 is an even number or 2 is divisible by 4, like we did in the previous example. But that wasn't entirely clear that that was the contradiction we were going to reach from the beginning of the proof. It just was a contradiction that we found. And so when you know that you're done with the proof by contradiction can sometimes be confusing to people. You don't really know what contradiction you're trying to reach, just anything. Last but not least, really, there isn't any particular thing about a statement that will scream, I ought to be proved by contradiction. In theory, every proof could be a proof by contradiction. There aren't any exclusions on when you can or cannot use it. However, it's just not always appropriate, and figuring out when a proof by contradiction is or is not appropriate is a real mathematical maturity. So for example, a lot of undergraduates learn proof by contradiction and they really start to rely on it heavily and try to do basically every proof by contradiction. This isn't really wrong, but there are plenty of times where people will aim to argue with a proof by contradiction and there's another proof technique that really is much clearer. And so figuring out when you should let go of proof by contradiction can be a difficult thing to master. So if you'd like to see an example of this, a time where proof by contradiction works but makes a proof harder than it really needs to be, you could take a look at the statements, if a squared minus 2a plus 7 is even, then a is odd. This is really something that is a lot easier to prove directly via its contrapositive. It's doable by proof by contradiction, but the proof will be a little bit messier than if you would prove it by contrapositive instead. So these are some things to keep in mind as you're working through proof by contradiction. They really are very lax, and at this point in time, if you've already studied direct proofs, proof by contrapositive, proof by cases, you shouldn't have too much problem with the structure. It's more a matter of practicing and getting acquainted with this technique.